Hello, everyone, and welcome to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, here we go. So, today we're going to be focusing our attention on temperature, energy, and the atmosphere, which really kind of combines what we've been leading up into here in section one. And so, we're going to add some new concepts, processes, and terms, and then also kind of like use or apply some of our previous knowledge. So we'll begin today's lecture podcast with a review of temperature and kind of just like really thinking about what temperature is. And then we'll kind of connect energy and temperature before we think more critically about the layers of our atmosphere. All right, so I thought it'd be good just to kind of take a moment. You could even pause the lecture and think about it in your own words. Like, what is temperature? So take a moment, kind of think about it. Write some notes, maybe even just words, phrases. What do you think? What is temperature? What's the definition of temperature? All right, coming back to it. So, what is temperature? It is a measure of kinetic energy of matter, which, what is kinetic energy? Well, kinetic energy is the energy of motion. So perhaps, at least when I first came to this and thought about temperature, I didn't immediately come to this idea that temperature is a measurement of motion, but in fact, it is. And so what does this look like, or how does this kind of work? So we're going to measure the amount of kinetic energy of matter, such as gas, liquid, or solid. We can, just as an aside or an addition, we can capture kinetic energy and transform it into things like electricity. So there's more and more capturing of wave energy being conducted around the world, largely in the ocean. So if you're curious, check it out. There's some cool articles about capturing wave energy. So let's kind of think a little bit more, or expand our understanding of this temperature and kinetic energy. And we can then focus here on heat. And so the term heat, at least within physical geography here, thinking about the amount of energy in the system. And so when there's high heat, high energy, there's lots of motion. When there's low heat or low energy, there's smaller amounts of motion. Like literally, the molecules and particles within this matter have more motion when it's hot and less motion or kinetic energy when it's colder. And so to kind of tie in or reconnect rather to some terms we thought of within radiation and global radiation, the term sensible heat is the quantity of heat held by an object that can be sensed by touch or feeling. So it's measurable by a thermometer. So sensible heat is often what we think about when we think about heat, right? We can feel it, it's hot or it's cold. So now kind of like leading and connecting these basic definitions into how we measure temperature at Earth's surface. And so surface temperature is a measurement of kinetic energy contained in a unit of space, so think volume, close to Earth's surface. And so we could literally measure the temperature of soil or the beach sand. And when we do that, we're measuring collectively the kinetic energy stored in 1 cubic meter. And so maybe like that would be a really large shoebox rather. But just kind of think about a box, right? A parcel, and you fill it with this material. And so really when we're measuring surface temperature, you're measuring that total amount of kinetic energy stored in a unit volume space, like a box. So then we can essentially do the same thing, or do the same thing, but for air. And so keep that like box perspective, if you will, like a volume, a parcel. And so now we're going to measure kinetic energy contained in a unit of space of air close to Earth's surface. And so near surface air temperature. we could then measure air temperature higher up in the atmosphere and very high. And later we'll talk about these major layers of Earth's atmosphere. And so here, if we're going to, and when you think about like weather forecasts, you look at the weather and they say, oh, it's going to be this temperature or that, cold, warm, whatever. Those surface air temperatures, actual stations that are monitoring air temperature, have to be at least 4 feet or 1.2 meters above Earth's surface. And so these official air temperature stations, like at the National Weather Service, for example, have to be at least this high. And that is because if they were closer, then they're also going to be affected by the radiation being emitted by Earth's surface. And so by placing these sensors up at least 4 feet away, you're isolating it. And then again, kind of come back to this box example, you're thinking about this kinetic energy stored in a unit space. And so you want to think air temperature, and you don't want to have that air temperature being affected by the properties like physical material or surface below. And so all of our air temperature stations are at least 1.2 meters above Earth's surface. Another thing you may or may not have seen, but often like in your backyard or something, you've seen these like classic basic thermometers. However, they may or may not be highly accurate. If this thermometer that looks something like this, or just like literally a thermometer, is affected or exposed to solar radiation, incoming electromagnetic radiation, like shortwave radiation, you're going to incredibly increase the amount of kinetic energy of motion in this thermometer. And so if you stuck this out in the sun, maybe it was like close to 40 degrees here, and then you stick it in the sun, your temperature, the measurement of kinetic energy would go way up. And so why is air temperature measured in an enclosure? It is to isolate it from that direct reception of kinetic energy. And so kind of just as an example, again, going back to heat and quantity of stored energy, as the sun would then hit literally the thermometer, you would be increasing the kinetic energy of that thermometer. And so it would show a higher temperature. However, if you were to only measure the air temperature and exclude essentially that incoming solar radiation, you could put it in something like this that literally keeps it dark and shaded, doesn't allow any direct insulation through, but is also very well ventilated. So the airspace is able to mix vertically and horizontally with its surroundings, maintaining this thermal equilibrium to measure, again, to go back just a little bit, this amount of kinetic energy stored within a unit space close to Earth's surface. So there you have it. That is why air temperature is measured in an enclosure. So many of us have seen Celsius and Fahrenheit, and perhaps also the unit of Kelvin. I mostly just want us to appreciate that there are 3 major units of measurement of temperature, and they are Celsius, Kelvin, and Fahrenheit, and each one has these kind of equivalents, if you will. And so to kind of just think about, here would be the temperature of the sun's surface in these different units here, and then the boiling point of water. So for Fahrenheit, 212 degrees, and then reference that to Celsius, then it's exactly 100 degrees Celsius. Our freezing points for Fahrenheit, as we're likely familiar, at 32 degrees, and then here's 0 in Celsius, whereas Kelvin has a different unit. I won't really expect that you need to be able to convert among these units, but just appreciate that there are 3 major units of measurement, and then many of our physical properties calculations related to transferences of heat may require that you be using one of these units. And then there is this absolute 0 that is kind of hard to achieve. And then, like Mr. Freeze says, it's time for you to chill out if you get down to that cold. So absolute 0 here, again, and just as a reference of Celsius, Kelvin, and Fahrenheit. Here are the equations that are the unit conversions to then go from Fahrenheit to Celsius or vice versa. And so you could simply apply these equations. If you knew the temperature as Celsius, you could multiply it by 9/5 and then add 32, and you would convert from Celsius to Fahrenheit, and then so on and so forth. So, as I said, I'm not going to expect you to perform these calculations on a quiz or an exam, but we might use them in an activity or exercise. All right, so have you ever heard of like a heat index or next wind chill? So in the summer, if you watch the weather forecast, often your meteorologist will describe that there's going to be this high heat index the next day. And this has everything to do with the amount of relative humidity, how humid or not so humid the atmosphere is. And so we're going to refer to some previous terms like latent heat, which is the exchange of energy that isn't quantified by a thermometer. So you can't measure latent heat with a thermometer, but nevertheless, there is an exchange of energy. And so when, for example, to kind of like think about what this feels like, why is there a high heat index? And so on a hot summer day, do you think it feels hotter when it's humid or when it's dry? If it was like 80 degrees, one day was really high humidity and the other day was really low. Well, if it's really high humidity, there's a lot of moisture in the atmosphere. And so inside of us, literally, like we're mostly water. And so, and when it's, then you're evaporating. And so if you have lots of humidity in the air near your surface, the rate of evaporation is really low. When it's dry, then, so conversely, if it's really dry outside, the rate of evaporation from your skin out to the atmosphere, from your liquid inside to the outside atmosphere, is much, much higher. And so that differential, so we're liquid inside, and if the air is really dry, you have lots of evaporation. And if the air is really moist or humid, that rate is much lower. And so whenever and wherever water evaporates, when it evaporates a lot, you're able, like humans or Earth, are able to shed a lot of energy. There's actually an incredible amount of energy coming from liquid, and then when it evaporates into gaseous phase, that gaseous phase is absorbing essentially, or the transfer of energy is going into the gaseous phase. And so you could effectively cool yourself. But when the humidity of the atmosphere is really high, there's much less evaporative cooling, and so it feels hotter. Like literally your body inside is not able to shed as much energy. And so if it was 80 degrees and really humid, your body feels like it's hotter because it's not able to shed that. And actually, really, like if you start sweating on a humid day, that liquid water is much slower to evaporate on your surface of your skin. So not only from inside to out, but that liquid water on your surface just kind of stays there as liquid when it's really humid versus when it's really dry outside, that liquid water like almost instantaneously evaporates. So now we can kind of like flip it around. So that was summer and heat indexes, or, you know, when temperatures are relatively high or warm. But in the winter, when it's cold outside, it could actually feel colder. And so it's the same concept or process, but flipped around. And so now in this case, literally in our atmosphere in the winter, and we'll explore this in a future topic in GC 100, the winter, cold air holds less moisture than warm air. And often our atmosphere is really dry in the winter, which means there's high rates of evaporative cooling. And so in the winter, it's cold, but also dry. And so your skin, like you're literally evaporating a lot. And so when it's windier, like literally the higher the wind, let's just say you're evaporating from your surface of your skin to the atmosphere. And as the wind blows, you're automatically like replenishing that air near your body with dry air. And so the little bit of moisture you add gets blown away, and it keeps this kind of dry air moving over the surface of your body. And so literally it feels colder because your body has this tremendous rate of evaporative cooling. So there's wind chill. So now moving into kind of this combined understanding of energy and temperature. So we'll start with a little bit of a review. And so again, the sun being a hot object emitting tremendous amounts of electromagnetic radiation, and in fact, really tremendous amounts of shortwave incoming radiation as insolation. And so these take the forms, at least near Earth's surface. The majority of this is between the ultraviolet, visible, and then near infrared spectrum of the electromagnetic radiation. And we've talked now quite a bit about absorption and re-emission, either by atmosphere, like greenhouse gas, or surface properties. And so then within our atmosphere, there's also a tremendous amount of emission of long wave radiation as thermal infrared radiation. And so what is net radiation? It's really just the balance between these two, the balance between incoming and outgoing radiation. So incoming shortwave dominant, outgoing long wave radiation. So now let's kind of like apply this on a landscape using a landscape perspective. And so do you think the surface air temperature, remember the amount of energy in a unit space near Earth's surface, do you think that near surface air temperature is warmer or cooler in an urban area when compared to a more remote or rural area? And so if you were to measure atmospheric temperatures in an urban environment in the atmosphere, and then you were to go like 30 miles outside of a city into a more natural landscape with fields and forests on the same exact day with the same amount of insulation coming in, which one do you think would be warmer? Well, if you thought it was the urban environment, you would be correct. And so because of the surface materials of urban environments like roads, buildings, parking lots, etc., and because those materials like a road absorb a tremendous amount of energy and then re-emit that energy as long wave radiation, that sensible heat is increasing the total kinetic energy in our atmospheric temperatures of the air in an urban environment can be quite a bit or considerably higher when compared to a rural area. And so this is actually referred to in a phenomenon known as the urban heat island. Literally, it is human-induced change to the landscape that causes a measurable temperature increase. And so all other conditions equal, because all of these roads and buildings are absorbing a tremendous amount of energy and then re-emitting that as long wave radiation, much more so than a rural area, you can experience like several degree Fahrenheit differences in temperature on the same exact day with the same exact conditions in a rural area when compared to a downtown urban area with lots of infrastructure. So now we're going to compare land versus water, or air temperature specifically above land versus above water. So kind of similarly, like the last example, on a given day with the same amount of input of incoming radiation, do you think the air temperature above the land or the water temperature above the water, or the water itself rather here, versus the land itself? Let's just tie it directly there. So if you put a thermometer in the ground right here in some bare soil, and then you put a thermometer in at the same depth in the ocean or a body of water, which one's going to heat up faster? Well, the land will heat up considerably faster, and let's explore why. And so water has a few unique properties that are much different than land. And so water, first of all, is semi-transparent. And so that radiation as insolation comes, it reaches the surface of the water, but then it's also allowed to pass down through into the water column, which is then distributing that radiation across a much larger distance versus that same amount of radiation coming in, especially reaching surfaces like bare soil, is hitting the soil. And while there's some reflection, and there's also some reflection on water, that surface is absorbing it almost right there at the surface. It's then absorbing it and re-emitting it as long wave radiation. So now that major difference again, which is really just the fact that water is semi-transparent. Another major difference is this fairly considerable amount of convective mixing that occurs within a body of water. Literally hot water, like hot air, hot water rises, it cools and it falls, and it literally just has its own natural convective system. So now you're actually like literally moving and redistributing this energy naturally due to these convective cycles, where the Earth does not do that, not like that anyways. And so the amount of this convective mixing that's occurring within water is tremendous. So now you're even like kind of redistributing and moving it around. Another very significant difference between land and water is that water has a very high specific heat capacity, meaning it takes a lot of energy to raise water by 1 degree Celsius, for example. So the higher the heat capacity, the longer it takes to heat up. The heat capacity of sand or barren soil, if you will, is much lower. So it means it heats up quicker. And so just those differences alone also delay this increase in temperature. And last but not least, as we kind of previously described with wind chill and heat index, and then more specifically latent heat exchanges. So water to air will have the most amount of evaporation possible because it is literally just liquid water, and there's a surface and then you have atmosphere. And so the most amount of evaporation will go right there. Where soil or surface that's moist has some water in it, but it does not have nearly as much water. And so there's literally like less evaporation. And so you have this great or higher amount of latent heat exchanges, again, which is allowing water to transfer energy from liquid into the vapor or gas phase here. So now let's tie these kind of like physical differences and think it more on a landscape, like physical geography level. So let's tie in kind of spatial components of this. And we really can do this when we compare a continental location versus a maritime location. So what is continental versus maritime? So continental simply are places located within a large landmass, meaning not anywhere close to large bodies of water. Versus a maritime, then the opposite is a location that is located within or very near a large body of water, like the whole west coast of the US and really both coasts, but largely our air systems are dominant from west to east here. And so we have this large mass of air over the Pacific Ocean, and this whole region on the west coast having this fairly dramatic maritime climate. So comparing locations near large bodies of water to locations further away or inland, away from large bodies of water. We have kind of like a mini maritime continental climate. I would say a microclimate more than this kind of like large scale. So Lake Superior and the Great Lakes in general are large bodies of water. And in Marquette, like physically in the city limits, we're very near Lake Superior. However, if you travel like 20, 30 miles inland to Ishpeming or Michigami, then you're now much further away from that water. And on any given day, that can then translate into these kind of fairly significant differences of temperature. In the winter, actually, it often looks something like the temperature of the air in Marquette City is warmer than Ishpeming or beyond Michigami. And then, so it's like, let's say it's 0 degrees Fahrenheit in Michigami, it might even be like 10 or even 15 degrees Fahrenheit in Marquette. This is a generalization, but it often is true day in and day out. The reverse is then true in places like Ishpeming in the middle of the summer. It's actually hotter, kind of going back to our last example, land versus water. And so land heating up much quicker. In the summer, continental locations are warmer and maritime locations are much cooler because of that proximity to water and the rapid rates at which land surface heats up. And so I have a good friend, lives in Ishpeming, works in Marquette, and he literally says like he'll be working in his yard or something in Marquette or in Ishpeming in the summer, and it'll be like 85 degrees Fahrenheit out in Ishpeming Township. And then he'll be like, oh, I'm going to Marquette. I better throw in my sweatshirt because so many times, like in the middle of the summer, it'll be like 85 degrees in Ishpeming, literally, and it'll be like 70 or 75 in Marquette. Well, maybe that's not quite sweatshirt weather. It is fairly considerable. So to kind of reiterate and reemphasize that on these larger scale maritime climates like the Pacific Northwest in Washington State, where I have been able to visit my brother here in Bellingham, Washington for many years now. And so here, this whole region really close to the ocean, and then here's what they call the Puget Sound, you have this maritime climate. And so it's a lot warmer on any given day, especially in the winter, then because of that proximity to the water, it's kind of moderating the temperature. Whereas when you move inland and really not that far inland, it gets much colder. And so this is degrees Celsius, with blue being colder and red being warmer. And then to kind of convert from Celsius to Fahrenheit, just for your reference, literally what this map is showing on any given day, on average in the winter, you're looking at like 15-degree Fahrenheit temperatures in eastern Washington and then across into Idaho and Montana, versus near the coastline, you have this kind of average of almost 50, so 49 degrees Fahrenheit. So now let's kind of add a temporal aspect. So we were thinking very spatial. Now let's think about what the temperature of the air would be like over the course of a year in a place like Bellingham or Seattle versus over in Spokane or another small town. And so let's kind of like drag that across time, if you will. And so here's January through spring, so March into May, June, July, etc., all the way till November. And so you could pause, and I just kind of want you to think about it in your own time for just a moment, to think about how temperature is different. And what I usually like to do with these kind of exercises or experiments for myself would be, I would say, okay, what do I expect the temperature to be in a continental location and a maritime location in January? And so you could kind of go back to this as an example. And then you could say, oh, I think the maritime in the winter is actually going to be warmer, and then the continental will be colder. And so you could start with a dot here and a dot there. You could do the same thing in spring, or really maybe just kind of compare, here's winter, and then right in the middle of summer, you could then think, okay, which location do you think is going to be warmer in the summer, a continental or a maritime? And then finally kind of just bring it back to whatever you thought in the winter. And it looks something like this. And so if you were able to stop and attempt this, you would draw, and this is just a conceptual diagram, but if you really looked at temperature profiles in these continental and maritime locations over the course of the year, they would look a lot something like this. And so to kind of combine some of this, thinking about maritime sensible heat transfer, in the summer, the warm air is cooled by the water, by that close proximity water. And so you have this effective cooling due to the proximity to water in the summer. So you have a cooler, cooler temperature in the summer right here. And then in the summer in the continental location, it should be considerably, or likely would be considerably warmer in a continental location. So that, again, surrounded by land, the land absorbing all of that radiation, then absorbing and re-emitting as long-wave radiation. And so then conversely here, you have warmer air in the summer. And then to focus on the winter here, in our continental location, we don't have that effective. So even though like our air temperature in the winter maybe isn't warm, it's much warmer in a maritime location, because water having that high specific heat, storing and retaining its heat, and then effectively warming what otherwise would be colder air. And so you have this warmer temperature in the maritime locations in the winter and colder in the continental. And ultimately, like if you just kind of focus on maritime climates are highly regulated or mitigated in the sense that there's very little change. The amount that it's warmer in the summer versus the winter is a smaller amount of fluctuation versus continental climates have a much higher amount of fluctuation, much colder in the winter and warmer in the summer. What about daily extremes? Well, really, you can kind of like do the same figure. It might have different ranges of temperature, but it would probably look very similar. So if this was midnight to noon to midnight again, you really would expect, at least in the summer when there's lots of radiation, something very similar where continental locations are going to heat up much more rapidly in the middle of the day, but they're also going to cool off at night. And again, because for the same reasons right here, that proximity in a maritime at night, you have that relatively warm water offering heat, like literally providing some, where the continental, then once the sun goes away, there's no longer this immense amount of absorption and re-emission of radiation, and therefore it then starts cooling off much more rapidly. Okay, so now let's think about our atmosphere and the structure, really the major four layers of our atmosphere, and to identify them here. And we will then subsequently talk a little bit or focus our attention on each of these major layers and their properties, their properties moving forward. Nearest Earth's surface down here, we are all in what is called the troposphere. And then as you go up in elevation, they will transition into the stratosphere, then to the mesosphere, and ultimately at the very top, before you reach outer space, you would be in the thermosphere. And we're going to focus on this temperature plot within each of our descriptions here. So just appreciate that there is a temperature profile from freezing. And so you're actually having warmer and it gets colder, and then it gets warmer again and colder again, and then warmer again. And we're going to explore why that is the case in each of these layers. So let's begin our journey in the troposphere, where we all live. And so it's the lowest atmospheric layer, and specifically it's where temperature decreases. So it goes from relatively warmer, and as you go up and up and up and up in the troposphere, it's getting colder and colder and colder. And so you have this kind of literally consistent decrease of temperature, and that consistent decrease actually is very well established as it is what's called the environmental lapse rate. And so on average, our air parcels decrease by 2.5 degrees Fahrenheit every 1,000 feet. This can vary a little bit over time and space, depending upon the composition of the atmosphere and the atmospheric conditions, like percent clouds. But ultimately, this is fairly reliable estimate. If you wanted to just like estimate what the temperature would be if you went up 1,000 feet, it would literally be likely very close to 2.5 degrees colder by going up by 1,000 feet. So as I at least just kind of highlighted anyways, within our troposphere, we have, at least compared to all of Earth's four layers that we'll now focus on, there are significant amounts of water vapor and aerosols. And that's a property that makes our troposphere very unique, where both of those capable of absorbing shortwave radiation and re-emitting as long-wave radiation, contributing to our greenhouse effect. So why does temperature decrease with increasing elevation? Like, why does it actually happen? Maybe take a moment, think about it. It really happens for two major reasons. One of them, literally, as you go further and further away from Earth's surface, you're literally going further and further away from a source of long-wave radiation emission. Just like moving further away from a fire, a bonfire, it'll get a little bit colder and colder and colder as you go away. So that's one reason. And then another major reasoning is due to the decreasing air pressure at high elevation. And so pressure affecting temperature. We'll explore that a little greater detail in a future lecture topic. So just to come back to the greenhouse effect one more time, at least for now, within this lecture. Just appreciate again, there's an incredible amount of moisture in our atmosphere, both in liquid as well as gaseous forms. And liquid and gaseous water has this incredible capacity to absorb radiation and re-radiate it as long wave radiation. And then also the winds blow. And so not only can you store radiation and it re-emits it, but that stored radiation can move over long distances, like literally across continents. And so you're also like transferring heat from certain regions, like the South or like equatorial Pacific region. You can transfer like all this heat that was contained and like stored actually is then moving from west to east, and you're going to like transfer some of that heat energy across thousands of kilometers or more. And so aerosols, also to kind of highlight, there's particles within our atmosphere. Those particles also absorb energy shortwave, just like sand or dirt or parking lots in that way. But the particle can absorb radiation and re-emit it, but it also forms a nuclei for condensation. So it also like promotes condensation or more water. So aerosols also being really important within the greenhouse effect. So let's just focus on this one unique phenomenon within the troposphere, which is called a temperature inversion. And it really is like it sounds. It's when a layer of troposphere temperature, so the temperature increases now with increasing altitude. Remember, we should be, or we expect the air to get colder and colder and colder. But then if an inversion sets up, it literally will, for a portion of the troposphere, the temperature profile reverses and it actually starts warming and warming and warming. And then that layer, it's literally an inversion layer, then it kind of returns back to normal after you go above this inversion. So what is an inversion and how does it happen? It happens for a few major reasons, but ultimately and simply, you have a cooler air mass sitting over a warmer air mass. And this often can happen in locations near an ocean, for that matter, where you have large air masses over the ocean. They're moving from west to east and they move over this relatively colder air mass that came above the water, now moves over the land and it sits over that warm air mass. And then you can like create this like literally inversion layer. And so cool ocean air masses are a very common reason why an inversion layer sets up. Something, and they can look really cool and sometimes like naturally. Here's literally a picture of an inversion sitting over the Grand Canyon. And you can even see this in smaller contexts here in Michigan where there's some topography, or you can see them in larger areas with larger topographic change, like the Intermountain West. So for example, when I lived in Moab, Utah, my tent that I lived in literally was at about 6,000 or 6,200 feet elevation. And then I worked in the town of Moab, and Moab was about 4,200, maybe 4,400 feet elevation. So almost a 2,000-foot change. And it had kind of topography similar to this picture. And literally I would drive in and it would look kind of like this picture. You would drive in and I'd be on a highway, and all of a sudden the road got to the break where you would start going down and you would literally drive right into the clouds, and then you go through a cloud band and then you go underneath and you go into Moab. Literally, I would have like driven something like this right through this inversion layer, and then I would get down into Moab where the air would literally be trapped and there would be this thick cloud band above me. It's kind of unique and really different. One thing to be concerned with, but actually did to some extent happen in Moab, although Moab is not that large. It's like the size of Nagani or something. But in much larger locations like Los Angeles or Salt Lake City, the larger cities, it suppresses vertical mixing. It literally keeps everything down near the surface and it doesn't allow it to like mix and get blown away. And so you can actually have these incredibly poor air quality events when these inversion layers set up. So to learn a little bit more, I encourage you to click and open this and watch this news article about poor air quality in Montana related to inversions. Some other examples include here, just kind of like visually, here's Seattle and here's Mount Rainier, and you can kind of see this inversion and this like suppressed vertical mixing, lots of particulates near Earth's surface and just some different areas. I mean, this happens the world over, in across Asia, and here's India, just thinking about particulate concentrations being incredibly high. And so this again kind of is localized, and it doesn't last forever. With the longer an inversion layer sets up and is maintained, the poorer and poorer the air quality gets, especially in these industrialized regions that have lots of combustion going on. It just gets trapped there. It doesn't escape. All right, so now let's keep going up, and we're going to talk about the pauses or the boundaries. The tropopause is the boundary between the troposphere and the stratosphere, the next layer, which we'll talk about next. And it is where temperature stops decreasing with increasing elevation, and then in the stratosphere, it actually does the opposite. It starts increasing with increasing elevation. The elevation, altitude of that tropopause is not consistent over space or time. And so literally the height of the troposphere can be really quite high altitude in some locations or some times, and then it can be much lower, like thousands and thousands of meters or even kilometers here. And that could be a seasonal difference, like in the winter for us in Marquette, Michigan. There is the tropopause is much closer to Earth's surface, and then in the summer it's much, much higher. And so because of that radiation emission and conductive cycling, then in the summer you have this lots of updraft and hot air rising, and it literally creates a thicker layer of the troposphere. And so higher elevations when it's warmer and lower elevations when it's colder. And then that, as you could think about other maps, like it changes as you go across the US from warm and cold regions, your troposphere is going up and down over space. So now let's think about the stratosphere a little bit. So within the stratosphere, so we're in the troposphere, it's warm, it's getting colder, colder, colder. We reach the tropopause, and now we're in the stratosphere, and actually our temperature starts increasing with increasing altitude. Major or unique different or like properties that are different than the troposphere. In this layer within the stratosphere, there's very little water vapor or particulates. It is then comparably much different, compositionally speaking, than the properties within our troposphere. It has much less water and particulates. However, it has much more ozone. And so we previously thought about the ozone layer and how it protects us from UV radiation. And so what does this look like? Think about, again, incoming insolation, incoming solar radiation. And then as that incoming solar radiation reaches the top of the stratosphere, the ozone molecules that are in our stratosphere are greenhouse gases. They absorb that radiation and they re-emit it as long-wave thermal infrared energy, which is sensible heat, which then is literally why temperature is increasing with increasing altitude. Then to kind of reiterate again, this layer provides humans and really all living organisms this incredible protection from really powerful or intense incoming ultraviolet radiation, because it's literally like effectively blocking it by absorbing it from reaching Earth's surface. So I kind of hinted at it, but why does temperature increase with increasing altitude? Well, it's because there's more UV radiation, and specifically UVB radiation, that's absorbed near the top of the stratosphere. And so the ozone layer being in the stratosphere. And so as this incoming solar radiation comes down and down and down, it reaches the top of the stratosphere. The most amount of that radiation is absorbed near the top and effectively re-emitted as thermal infrared energy, as sensible heat, causing the temperature to be the warmest near the top because there's the most re-emission of that absorbed shortwave radiation that then was emitted as long wave. And as it goes down and down and down, there's less absorption, less absorption, less absorption. And because there's less, then there's less re-emission as long wave radiation. And so therefore, the temperature gets warmer and warmer and warmer as you go up within the stratosphere. So at the very top of the stratosphere, you reach what is known as the stratopause, and this is where temperature ceases to increase with increasing elevation, and then you reach the mesosphere, where temperature here, as you can see, starts once again to decrease with increasing elevation. So the mesosphere, some unique properties are it is the coldest atmospheric layer. And so it's going to get colder and colder and colder as you go up in the mesosphere. Often this is where we're seeing our meteors interact with our atmosphere. And as it says here, the major property being temperature is decreasing with increasing altitude, and it is the coldest atmospheric layer. So then you reach the top of the mesosphere, which is the coldest part, and temperature stops decreasing with increasing altitude. And then we reach the thermosphere, where temperature starts increasing with increasing altitude or elevation. And for a moment, if you kind of look at this graphic, and while you can't hardly see the actual temperatures, like just as a relative comparison, here is an average temperature near Earth's surface. And then if you go up, and you can notice that the temperature is much, much warmer in the thermosphere, at the top of the thermosphere, than it is near Earth's surface. And so, in fact, it goes from the coldest right at that boundary at the mesopause to the hottest or warmest at the highest point of the thermosphere. So now we once again have increasing temperature with altitude, and a unique property of this layer is gas molecules like oxygen and nitrogen are incredibly far apart. And so the distance between individual molecules within the thermosphere can literally be several kilometers, which is so very incredibly different than within the troposphere, where we're just surrounded by molecules all the time. And so this distance is why this temperature condition exists. So we're kind of getting into it. So why then are there extremely high temperatures? I mean, these are really, really high temperatures that aren't even experienced near Earth's surface. Like, why does that happen? And do you think it feels warm? They're kind of interconnected. And so here then, within the thermosphere, you have these gas molecules that are very far apart, but that one molecule is absorbing this tremendous amount of incoming solar radiation. There's nothing blocking it. And so that one molecule has extraordinary kinetic energy. Remember, temperature is a measurement of kinetic energy. And so that one molecule has extraordinary kinetic energy, and that's why there is really, really high temperatures. However, if you were like literally floating around up there in the thermosphere, would it feel warm as sensible heat? No, because like think about this distance. You could be several kilometers away from the nearest molecule, and that's what you would then like feel by sense or touch some radiation then. And so even though you have this incredibly high temperatures, it does not feel warm, and has everything to do with this great distance between molecules. But the temperature then has everything to do with the fact that that one molecule has this unbelievable amount of kinetic energy. All right. So to kind of wrap it up and think about something really pretty that perhaps some of you have seen, we can think about our aurora borealis, which is what happens when cosmic radiation interacts with the ionosphere, which is a layer of atmosphere within the thermosphere, where cosmic radiation is ionized by within, and it creates what we know as northern lights. So I hope perhaps if you've never been able to see or observe the northern lights, someday you will. Just got to get up usually in the middle of the night and go look up in the sky. So with that, Dr. VG is signing off.